Hello, this lesson covers sections 1.1, 1.2, and 1.5 in honors geometry. We're going to start out with some terminology we should know. A point is a location in space. So a point is just a dot on a graph, and it's named by a capital letter. So we could have a point somewhere, and it would be listed like this, and we would call it point A. We also could just write it as A when we're referring to the point. A line extends infinitely in two directions. Infinitely meaning forever. So we show that with arrows in two directions. So a line has two arrows on it, and it has an infinite number of points, but we use any two of those points on the line to name it. So if we had an A and a B as points on that line, I could call this line AB, and I do that with putting a little line above it. Another way you can name a line is by a lowercase script letter. So there may be like a little L off to the side here, in which case this would be line L. A line segment is a portion of a line. So a line segment has endpoints. So if I took the same picture from our actual line and only wanted to talk about what was happening between there and there, that would be a line segment. And we write it the same way we would do this, except instead of putting the arrows on it, we leave it blank. Points cannot be measured because they're just a specific location. Lines cannot be measured because they go infinitely, but line segments can be measured. You can actually tell how long a line segment is. A plane extends infinitely in, I shouldn't say all directions, but it's a flat surface. Let's put it that way. A flat surface extending infinitely. And usually planes are written, or I should say drawn, as almost a parallelogram looking thing, infinitely. So they might draw it like this, and they can put a bunch of information inside the plane. The plane itself could be what we're talking about. We could name it by any 3 points on the plane. So let's say there was a point A, a point B, and a point C. We would call that plane ABC. Even if there were 20 points listed on our plane, we would still just pick 3 of them, as long as they did not form a line with each other. Also, there could be a script letter in the corner, in which case you would call it plane R. So we know that's not a point because it doesn't have a dot next to it. An angle is what is formed when 2 lines or rays intersect at a point called the vertex. I'm going to say rays for our purposes right now, intersecting at a point, the vertex. So our angles look something like this, where the point where they intersect is called the vertex. We could also name these by 3 letters, the same way we did a plane, but the order is very specific. So if I had a point A, a point B, and a point C, I would have to say ABC or CBA because the vertex point has to be in the middle. So we use an angle symbol, either drawn like this or a little curve inside, and then we would say the 3 letters. If there's only this angle existing and we don't have an extra line coming out, we could actually also call it just angle B. Just the vertex is fine as long as that's the only angle happening at that vertex. But also, there might be a number inside. They might just put a number without a degree symbol because angles can be measured as well in degrees. In this case, we would just call it angle 1. So now we get to some more relationship terms as opposed to actual item terms. Congruence is the mathematical idea of things being the same. So normally if we're talking about values of things, the measures of things, those could be equal to each other, but when you're talking about an actual physical structure like a segment or an angle, those would be congruent to each other. And the symbol for congruent is an equal sign with an additional curve above it. Segments can be shown to be congruent using dashes. So this segment and this segment are marked as congruent because they both have the same dash. We could also mark angles as congruent using curves in the corner of the angle. So I'm saying this angle here is congruent to this angle here. Bisect is exactly what it sounds like. Bi in two, and sect like dissect. So to cut into two but equal pieces. Two equal or congruent pieces. Parallel are when two things never intersect and they're on the same plane, or they themselves are planes. So I'm going to say coplanar and doesn't intersect. There is actually a name for lines or segments that are not coplanar and don't intersect. So that's why we're specifying specifically here coplanar. We again have a symbol, just like we did for congruence. The symbol is a pair of segments that look like they are parallel to each other. And we mark parallel by actually using a little triangle symbol or a little arrow symbol on the lines themselves. So these both have these little triangle arrow marks on them. That's what tells me that they are parallel to each other. And our last term here is perpendicular. And perpendicular means to intersect at a right angle. A right angle is an angle that is 90 degrees. The symbol for perpendicular is an upside down T, right? If I look at these lines here, they actually form right angles when I draw them. And to mark perpendicular on a graph or on a picture, we would put the right angle symbol, which is a little box in the corner. And that's how I would know that lines are perpendicular to each other. These are some postulates, which is a fancy word for math fact, that are important to know but not really important to memorize. So one is that through any 2 points you can form a line, and that also means every line has to contain at least 2 points. When two lines intersect, they will always intersect at a single point. Every plane contains at least 3 non-collinear points, and if you have 3 non-collinear points, they will form a plane. If 2 points are on a plane, then their line is also on that plane. And when 2 planes intersect, it is actually in a line. So when 2 lines intersect, it's in a point. When 2 planes intersect, it's in a line. So a very important part of geometry is being able to create diagrams based on information given to you in the problem. So we're just going to practice drawing a diagram to match the information they've given us. So I'm going to start here, plane R. So already I know I need to draw some sort of shape. And I'm going to put a little R somewhere in the corner to know that it is called plane R. And it contains 3 lines, line AB, line CD, and line EF. But there's more information about those lines. Line AB is parallel to line CD. So I'm going to draw 2 lines that don't intersect each other. And I'm going to label one with the points A and B, and one with the points C and D. And I'm going to mark that they're parallel to each other by including those little triangle symbols on them, because it's important that when you are given information in the problem, you mark that kind of information on the picture. We are also told line CD is perpendicular to line EF. So line CD here, I'm going to draw another line. Nope. I'm going to label 2 points on that, E and F. And I'm going to include the perpendicular symbol to show that it was perpendicular. I could have extended this line. It could have crossed AB. There's nothing saying that it doesn't cross AB, but I just drew it exactly as the information told me. So the next example, we want to give another name for angle 1, state the vertex and the sides. So the first thing I'm going to do is find where the 1 is in the picture. And the 1 is in the corner right here, right? This is the corner that 1 is in. So if I were to draw the sides of that angle, we have XU is a side, which is a ray. I'm drawing it with the arrow going in just one direction because it is a ray. And the other one would be either xy or xz. It doesn't matter which. The vertex, the point where angle 1 is happening, is at the point x. And that makes sense because x was the first letter in both of my sides. And now another name for angle 1. So we said we could either name it by just the vertex, but in this case that's not going to work because at point x there's another angle here, there's another angle here, there's another angle here. So we can't name it just by x right now. So I'm going to have to use 3 letters. So I could either call it uxy, I could call it yxu, I could call it zxu or uxz, as long as I'm using 3 letters and that x, which is the vertex, is in the middle. There's a try problem here that you can do if you'd like, pause it if you want, and answers are posted online. Example 3, list the segments that are congruent to segment AH. So AH, if I identify in the picture where AH is, A is here, H is here, it's this segment right here. And I see that it has 2 dashes on it. So any other segment that also has those same 2 dashes on it will be congruent to AH. I know AB is not because it only has 1 dash. I know BH is not because it had 3 dashes, but HG had 2. GF had 2, and FE had 2. So these are all the segments that are congruent to segment AH. If I wanted to write something called a congruence statement, that would be segment AH is congruent to segment HG, or something like that. For example 4, we want to find the measures of the specified angles and identify any angles that are congruent and mark them in the diagram. So what I like to do is before I even find these, I pick either the top row of numbers on my protractor or the bottom row of numbers, and I put by each of the points what is the number that it went through. All right, so the x, I'm going to stick with all the top row. So x went through 0, y went through 40, v went through 90, W went between the 130 and the 140, so we'll call that 135 because it was exactly in the middle, and Z went through 180. The easiest way to measure these angles is to find the difference between the 2 values that go for the sides. So YOW takes me from 40 to 135. So that is a difference of 95 degrees. Oops, that was way bigger than I thought it would be. Put my 40 back. Okay. So the next one is XOY. So we're going from X to O to Y. So that's a difference of 40. VOW. So VOW from 90 to 135 is a difference of 45. WOZ is from 135 to 180. That is also a difference of 45. And then YOZ is a difference of 40 and 180. That's 140 degrees. That's yellow. Sorry, that's not great to be seen. So the last part is to mark the congruent angles in the diagram. Identify any angles that are congruent and mark them in the diagram. So when I look at the values of the angles, the measures of the angles, angle VOW and angle WOZ both had measures of 45 degrees. So I can say that angle VOW is congruent to angle WOZ. And so VOW, that was the angle in this corner, is congruent to WOZ. That's the angle in this corner. So remember, we're using little curves in the angles to show that they are congruent to each other. Here we have the angle addition postulate. So it's saying that if P, point P, is in the interior, inside the angle, then the sum of the 2 smaller angles formed adds, right, sum adds to the bigger angle as a whole, right? The sum of the two smaller adjacent being next to each other, sharing a side, angles, is equal to the measure of the whole angle. So I have ray SA bisects angle RST. So I'm going to start by drawing a nice big angle RST. I'm going to label R, S is the vertex, T. And then somewhere inside there we have ray SA. And actually, it cuts it exactly in half. So I'm going to mark those two pieces as being the same. Then it tells me B, point B, is in the interior, is inside angle AST. So here's angle AST. Somewhere in this angle, point B exists. So I'm going to draw ray SB. And now it tells me that the measure of angle ASB, see this little M in front? That stands for measure. That's when we're talking about the actual value of the angle. The measure of angle ASB is 11 degrees. So ASB, we're going to put 11 inside here. And BST is 25 degrees. They're asking us to find the measure of the entire picture. So the first thing I know is that together, if I use the angle addition postulate and add the two smaller angles together, this larger angle is 36 degrees, right? 25 plus 11 is 36. And now it takes me to the last part where it said bisects. So if this was 36, this would also have to be 36 because the angles have to be congruent. So for the whole big angle, that's a 36 and another 36, the measure of angle RST is 72 degrees. This is another try problem. Pause if you'd like. Answers are posted online. Segment addition postulate. Much like the angle addition postulate, we're saying the sum of two smaller pieces of segment is equal to the whole thing. So for this one, if a point is between two others, so here, if D is between A and R, so that means all on the same segment, I had points A and R, and between them existed point D. So AD, the length of this part, plus DR, the length of this part, equals the whole thing AR. It's very important to know the names of these theorems and postulates because we will be using them in the next chapter once we learn how to prove things. We're going to do something called proofs. So let's find the measure of yx. So yx is here. Let's make it a variable if we'd like. Let's call it x. These markings here tell us that these two things are congruent. So I can also make this part x. And using the segment addition postulate, this segment plus this segment would equal the whole thing. Or I could have just taken that 8.8 and divided it by 2 because I knew it was split equally. So I'm going to say yx equals 4.4 millimeters. Notice when I wrote yx this time, even though it was a segment, I did not put the bar above it. So just like when we talked about measuring an angle, I put the m in front to show that it was the measure as opposed to the angle itself. When I'm talking about the measure of a segment, I don't put the bar above it, I just use the two letters. Example 7. So we have a lot of information up here about what points are between what other points. So before I even sketch my actual segment, I know B is between A and E. So I have an A and I have an E, and somewhere between them is a B. C is between B and E. So here's my B, here's my E, somewhere between those is a C. D is between C and E. So here's C and E, between those is a D. So I've used all the letters they've mentioned. This is the order they will appear on the segment. So now I will draw a segment to match the order of these points. So we're going to say A, we're going to put a B, we're going to put a C. Ooh, we don't want that highlighted. C, D, and E. And now I have some additional information that I'm going to mark in the picture. AE is 38. When I want to show the length of a segment that's made up of more than those 2 points, I'll often use brackets that look like this to show that it went from one end to the other. All right, some diagrams will have that. others will have a curly bracket like this. That's usually what I'll draw when I'm actually physically drawing a picture. We also know that BD, from B to D, so starting here to here is 15. And also segment BC is congruent to segment CD is congruent to segment DE. So BC, CD, and DE are all congruent. So the first part of this problem that I would do is I would take the fact that BC and CD are the same, and they also add to 15. So if I cut that 15 in half, each of these is 7.5. And because this is congruent to them, it is also 7.5. So I want to find the length of AD. In our picture, AD is made up of these three smaller pieces, AB, BC, and CD. But also, AD is everything of the segment except DE. So I'm actually going to set up the segment addition postulate to be AD plus DE equals AE. We don't currently know AD. I do know DE is 7.5, and I know the whole segment AE is 38. So all I have to do is subtract 7.5 from 38, and AD equals 30.5. Example 8. Find the value of n and yz if y is between x and z. So again, I'm going to draw this out. There's only 3 points, so I don't have to worry about really figuring out the order here. I know x and z are the endpoints because it's between x and z, and y is somewhere between them. I also know that xy from here to here is n squared minus 5n. From y to z is 2n minus 8. And then the whole thing is 20. So using my segment addition postulate, I'm going to take the sum of the two smaller ones and set that equal to my entire length. So this is actually a quadratic equation because there's an n squared in it, and I also happen to have regular n terms. So the way I'm going to have to solve this is by factoring or quadratic formula. In our class, we're going to stick with factoring. I'm not going to give you any problems that require the quadratic formula. So I'm going to simplify this, and when we want to solve by factoring, we want this side over here, where the 20 is, to be 0. So I'm going to move it over by subtracting it, but I'm also going to combine my like terms. So this is really n squared minus 3n minus 28 equals 0. If you don't remember how to factor, we're looking for the two numbers that multiply to negative 28, like negative 28 and 1, negative 14 and 2, negative 7 and 4, and then we start repeating negative 4 and 7 and so on. And I am looking for them to add to negative 3, so the bigger number has to be negative. And it happens to be negative 7 plus 4 equals negative 3. So my factored form is n minus 7, because that was a negative 7, n plus 4, because it was a positive 4. So factored form is here. That means my solutions are found using the zero product property by setting each of these equal to 0. So n minus 7 equals 0 really means n equals 7. N plus 4 equals 0 really means n equals negative 4. It is possible that both of these work. So what I really have to do is go back to the original picture and plug values in. As long as the segments stay positive, even after I plug the number in, that value is a solution. So if I took the 7, I'm going to plug them into this side because that's the easier one to work with right now. 2 times 7 is 14, minus 8 is 6. Perfect. If that's 6, that's 14. This works. So n equals 7 is a solution. If I try negative 4, 2 times negative 4 is negative 8. Negative 8 minus 8 is negative 16. I cannot have a segment that is negative 16 units long, so that's out. It's an extraneous solution. So this is the last try. If you would like to do it, pause. If so, answers are posted online. And that is our first lesson of 1-1, 1-2, and 1-5.